Oh, welcome back, everybody. Welcome, welcome. Today we're going to be doing section 5.2. This is a fun section. It's all about comparing asymptotic behavior. We're going to talk a little bit about hyperbolas. We're going to compare the growth of these different functions. CS majors, this is a section that I think you will love. You will talk about these ideas even more explicitly in your CS courses. The stuff in this section shows up all the time in math and science, even shows up in my own research. So I'm excited to help you all learn it right now. Let me get the slides pulled up and let's get going. There we go. Okay, so quick overview. We're going to start by talking about hyperbolas. There's my laser. Hyperbolas. Then we're going to compare asymptotic behavior, talk about what that means. We will learn about big O notation. Then we're going to see some common types of asymptotic end behavior, and then talk about applications on the mathematical horizon at the end. All right? That's the idea. So let's get started. Hyperbolas. Before we get to talking about asymptotic behavior, we're going to introduce the last conic section, which is the hyperbola. We've actually seen the other conic sections already in this course. They're like baked into the course. Those include the circle, the ellipse, the parabola, and now the hyperbola. I talk a little bit more about these in a supplementary section at the end of the course, a little more geometric interpretation. But we're also going to study the circle a little more when we get into chapter 6, just to kind of prep us for trigonometry. But we talked about the circle, we talked about the ellipse, talked about the parabola quite a lot. So all that's left is the hyperbola. These things are called conic sections because you can produce their graphs by slicing two inverted cones with a plane. So just to kind of do a quick sketch, if you had imagine you had two cones that were like stacked on top of each other like this. Well, if you slice that pair of cones in different ways, then the graph you will produce will be the graph of these figures, these conic sections. So if you slice it this way, you're going to get a circle. If you slice it at a bit of an angle, then you're going to get an ellipse. You'll see like an elliptical shape. If you slice it like this, then you'll get a parabola that kind of goes like that. And then if you slice it like so, you will get a hyperbola, which is what we're going to talk about right now. All right. The reason that I'm talking about it right now is because hyperbolas are the only conic section that exhibits asymptotic behavior, which we'll see in a minute. So, what is a hyperbola? This is the definition. A hyperbola is the set of points in the plane R2 where the difference of the distances from two fixed points called foci is constant. Okay, so that's a bit of a geometric definition, but basically you're looking at the distance from two fixed points. We call them foci. They're each a focus. And we're looking at the difference between those distances, and we want that difference to be constant. I'll give a formula in just a minute, and I think the formula, the structure, will look kind of familiar. Some details about it. This is what I'm sorry, a hyperbola looks like, roughly speaking. There is a line that passes through like this. This is called the transverse axis. This is the line that contains the two focuses, the foci. Here's a focus, and there's a line that passes through just like so. The midpoint of the line segment that connects the two foci is called the center of the hyperbola. Makes sense. It's the middle point, you could say. There's another axis right here. This one's perpendicular to the transverse axis, and this is called the conjugate axis, right? There's that word again, conjugate. A hyperbola consists of two separate branches. Here's one branch, here's a second branch. And when these branches intersect the transverse axis, you get points that are called vertices. So this is a vertex, and this is a vertex, kind of like that. I don't say it here, but one thing I want to point out is that these branches are actually not parabolas. So beware. They might look a little bit parabolic, but they are not parabolic. They are hyperbolic. There's a reason, and that has to do with the asymptotic behavior of the graph of these objects here. Parabolas do not have the same asymptotic behavior as a hyperbola. So this is not just two parabolas turned on end like that. All right, just want to make that point. So Let's look at a formula. So that was defined geometrically, and what I'll do in the supplementary section is I'll derive this formula. But if you use that geometric definition and the definition of distance, you can derive this formula for a hyperbola. So this is the equation of a hyperbola that's centered at the origin, 0, 0. Its transverse axis is the x-axis. Its foci are at the 2 points negative c and positive c, and its vertices are at the points negative a and positive a. And this is the formula for that hyperbola. A little detail down here. There's these two numbers here, a and b, and those are the same numbers that you see here. And the equation to help you find the foci is given here. You might notice that it is kind of similar to the Pythagorean theorem. That is not a coincidence. That is actually a fact of the construction, but I'll go into those kinds of details in that supplementary section if you're interested in. What I'm more interested in you making sense of is this formula right here. Notice that the formula is very, very similar to one that we have seen before. In fact, I think I talk about this a little bit more. Um, it looks a little bit like the formula for an ellipse. The difference here, pun intended, I guess, is that this sign is negative instead of positive. All right. So here's roughly what one of these hyperbolas looks like. All right, here's a specific example. So this is the hyperbola given by this equation right here, x over 3 squared minus y over 4 squared equals 1. And you can kind of see where these numbers come into play when we're doing this graph. Here's negative 3 and 3. It's associated with that right there. We're squaring this, right? So that's where the plus and minus is coming from. There's 4 and negative 4 coming from there. And then 5 and negative 5 here, those are coming from that formula right here. B squared equals C squared minus A squared. Or in other words, A squared plus B squared equals C squared. If you move A over to this side, it'll be A squared plus B squared equals C squared. Okay. So there's an example. Here is the formula or the equation for a hyperbola centered at the origin where the transverse axis is now the y-axis. So this one is kind of opening up and down instead of left and right, right? Just like that. Um, Same kind of deal, but notice there's a slight difference in the formula. Now it's y over a and x over b instead of the other formula, which was this one. I'll flash back. This was the previous formula. X over a, y over b. Now it's y over a, x over b. You see that? Very similar. The formula to help you find the foci is unchanged. Okay. Here's an example. This is kind of the same example, but almost rotated. Um, no, I guess it is rotated. But here, notice that the transverse axis is the y-axis, just like that. There's the 3 giving you the positive and negative 3. Here is that 4, which is going to give you negative 4 and positive 4 right there. All right. So that's the basic idea of the equation. So there are two equations here, this one and this one. Here's some tips to help you remember what it will look like. What you really want to know is roughly what this should look like based on this formula or this formula. So the term on the left side of the negative sign is always associated with the transverse axis. So what that means is that the transverse axis will be the x-axis. With this one, the transverse axis will be the y-axis. So it's whatever term is on the left of that right there. Okay. A is actually the distance from the center to one of the vertices. So this number here tells you how far one of the vertices is. All right, or both of the vertices, I should say. C is the distance from the center to one of the foci. And if you wanted to compute that distance, you need to use this formula right here. B is going to help us draw what's called the fundamental rectangle. We'll talk about that in just a second. But here is an interesting fact. So since a difference of positive terms is being taken, right, we're doing a difference, not a sum, right? There's no bound on how large x and y can be for a point to still lie on the hyperbola. This is something very different from when we were looking at the formula for an ellipse. There was a constraint, right? When we had an ellipse, this was a positive, this was a sum, and this was saying that the sum of these two things was 1. So that's a very tight constraint. Here, we're doing a difference. So there is no constraint. And as a result, hyperbolas are unbounded. They're unbounded, unlike an ellipse. Yeah, hyperbolas are unbounded. And in fact, it has asymptotes, meaning that it is asymptotically equivalent to something, which we're going to see in just a moment. So here is the punchline. This hyperbola has two slant asymptotes, and the slant asymptotes are given by this formula right here. Y equals negative b over a x, plus or minus b over a x, my bad. And then here, this one has asymptotes plus or minus a over b x. So these are basically the asymptotes that the hyperbola is kind of hugging as it gets larger and larger, or as x and y get farther and farther away from the origin. Let me throw up that picture again so you can kind of see. These were the hyperbolas that I showed in the previous figures, but now I'm pointing out the asymptotes themselves. So there's this asymptote, which is negative 4/3 x, and there's this asymptote, which is 4/3 x. Now, here is that similar hyperbola. This one is negative 3/4 x. Notice that the slope is negative, right? So it's going down. And this one is, oh, this little typo right here. That should be a plus. This one is positive, so that's positive 3/4 x. There we go. So what I'm saying is that these hyperbolas are asymptotic to those two lines, which is something not present with a parabola, right? Well, kind of like we saw before, parabolas, they don't level out at lines. They keep going in a parabolic structure off to infinity, right? But what I want to do is I want to prove that these hyperbolas are in fact asymptotic to these lines. They also don't cross the lines, but let's just prove that they're asymptotic. And we're going to use some techniques that we saw, or at least a definition we saw earlier in the course in section 3.9, last time we studied asymptotic behavior. All right, so we're going to prove the first equation. We're going to start with this one, and we're going to massage things a little bit. Now, since x is not equal to 0 for any point on this parabola, we can manipulate this equation like so. I'm going to expand these two terms, expand these two expressions, I should say. So we'll get y squared over b squared, x squared over a squared minus 1. So really what I'm doing is I'm just kind of shifting things around, isolating this term, and then moving everything else away from it just like that. Yeah. Now what am I doing? Multiplying both sides by b squared puts a b squared over here and cancels the one there. Now I'm going to be a little bit tricky. So this might seem a little bit weird, but what I'm going to do is I'm actually going to factor out x squared over a squared from this term and this term. And when I do that, factor out the x squared over a squared, this term becomes 1. I took out the whole term, right? And this term becomes a squared over x squared. Again, if you do this kind of factoring, you can always multiply it back out to see if you did it right. So if I multiply this times 1, I get that. Check. If I multiply this times this, the a squareds and the x squareds are going to cancel, and I get 1. Check. So this is a valid factorization. This is actually the reason why we needed x to not be 0, because you can't divide by 0. So that's why that's there. Now what I'm going to do is I'm going to take the square root of both sides. So I'm going to take the square root of both sides. Remember, anytime you ever take a square root, you have to include a plus minus, which I'm doing right here. So when I take the square root of this, I'm going to get b over a times x, plus or minus. And then I'm going to get the square root of this whole thing right here. All right, so all I really did here was solve for y. That's the punchline here. I just solved that for y. And now what we're going to do is we're going to show that this is asymptotically equivalent to plus or minus b over a x. All right, remember that little like squiggly line that we talked about earlier? We're going to do that. And remember, two functions are asymptotically equivalent if the limit as x goes to plus or minus infinity of their ratio equals 1. Right? If you forgot about that, you can go check it out in section 3.9 where it's defined, okay? But that's what we're going to do. We're going to show that this is asymptotically equivalent to this. We do need to use one calculus result, and that's actually just the continuity of the square root function. In this case, that's going to let us move the limit operator inside the square root. So you'll see that on this step right here. but let's go through it. This is the definition of the definition you need to verify to show that things are asymptotically equivalent. So we're looking at the ratio of these two things. Y is equal to that formula right there. Now, when we divide these two things, we're going to simplify. Oh, remember, x can be very, very large in size. So here, these two things cancel completely. And then what we're left with is the limit of this square root. That's all we're left with. We're going to move the limit operator inside the square root. That's the calculus result there. The limit as x goes to infinity of 1 is 1. And then here, we're going to take the limit of this. But as x gets larger and larger, this is something you'll explore a lot in Calc 1. X gets larger and larger here. This term is going to go to 0. So the limit is actually 0. This thing right here is equal to 0. Square root of 1 minus 0 is the square root of 1, which is 1. And voila, we have shown it. This means that y is asymptotically equivalent to plus or minus b over a x. In other words, those hyperbolas are asymptotically equivalent to those asymptotes, those slant asymptotes. Okay, so here's just like a quick summary. This thing right here, the asymptote is plus or minus b over a x, or the asymptotes, I should say. This should say asymptotes are uh, there we go. Those are the two asymptotes. So this one, these will be the two asymptotes, and for this one, these will be the two asymptotes right there. A little bit of a pro tip: if you want to remember these formulas, it's not as hard as it seems. You might already feel overwhelmed, like, oh my gosh, how am I going to remember all this stuff? Look for the patterns and look for the little details that reveal the structure, right? Remember, these are slant asymptotes, they're lines, and so they have a slope, right? And what is slope? Slope is always rise over run. It's always the change in y over the change in x in this context, right? So that's why you're getting this structure of b over a here, because this b is associated with y and this a is associated with x. So it's like the change in y over the change in x, like so. But over here, a is associated with y and b is associated with x. That's why you're getting a over b as that change in y over change in x. That's really all it is, okay? So this structure is not too difficult to remember. And if you want to know the asymptotes, you're just doing rise over run, rise over run. That's it, and then you've got it, plus or minus, because you've got two of them, okay? So now how are we going to graph these things? So this is where we're going to talk about the fundamental rectangle, talk a little bit about the geometry. So if you remember when we talked about ellipses, those numbers a and b, they result in a stretch or a compression, right? Vertically and horizontally, depending on if you're talking about x or y. Same situation here. There's a vertical and horizontal stretch or compression going on, just like we saw earlier on in the course. The value that is associated with x, in this case it's a in this picture, that'll result in a horizontal scaling. We're affecting the x values, so we're going to do something horizontal. The value associated with y is going to be a vertical scaling because we're affecting the y values. So this is resulting in something vertical, this is resulting in something horizontal, right? And excuse me, what's really cool is these numbers a and b allow you to immediately construct what's called the fundamental rectangle or the central rectangle of the hyperbola. And that's this thing that you see right here. Okay. Let me zoom in a tiny bit. May need to go to here. Let me do this. Here, we'll do it a little bit better here. Okay, you can kind of see it. Yeah, yeah. Maybe I can get both. Well, kind of. Let me do this. Okay, so with this hyperbola, notice it's x over a, y over b, right? So look at this rectangle now. You've got a's right here and b's right here. So these numbers, these numbers a and b, basically define the fundamental rectangle. So here, this is negative a and a. Those will be like two midpoints of the sides of the rectangle. And then negative b and b will be the other two midpoints of the rectangle. And once you have those 4 points sketched, you can sketch the rectangle itself. And now here's the part I think is the funnest. Here's the cute part. If you draw the diagonal through the corners, the diagonals through the corners of that rectangle, those are the asymptotes. And then you can just graph the hyperbola by asking what is the transverse axis and sketching it like so. So it's actually easier to sketch than you might imagine. You just do this fundamental rectangle and then draw the asymptotes and then just ask yourself what's the transverse axis, and then you can just kind of hug those asymptotes and go off like that. That's about it. Um, Maybe similarly for an ellipse, it would actually be this. For an ellipse, it would be inside the fundamental rectangle. Okay, cool stuff. Very convenient, I find. So now let's do an example. Let me throw these back up here like that. I want you to try this example on your own, okay? Now that we've just talked about it, I want you to find the asymptotes and draw a sketch of this hyperbola by drawing the fundamental rectangle. So think about it for a minute. All right. Now you got to verbalize something. Say something out loud to yourself, to your friend, to your dog, to your cat, to your hand, something. Maybe a rubber ducky. All right. Now work it out on your own. My tip to you, draw the fundamental rectangle. Ask yourself what's the transverse axis, or draw the fundamental rectangle, draw the asymptotes, and then ask what's the transverse axis to sketch the hyperbola. All right, here we go. Okay. Yeah, I'll use my slides for this one. Okay. So notice here, this is on the left side of the negative sign. So the transverse axis is going to be the x-axis. This number is 3, this number is 2. So immediately we can plot the points -3, +3, and then -2, +2, and then connect them like so. And that's our fundamental rectangle. Boom. Next, we're going to sketch the asymptotes like that. And then if we want to know the equations of those asymptotes, we just think rise over run, okay? So it's going to be 2 over 3 plus or minus. That's the slope, right? So the equations of the asymptotes are y equals plus or minus 2/3 x. That's it, okay? Boom, boom, boom. Now, because the transverse axis is the x-axis, our parabola should look something like this. Something like that, very roughly. Okay, here we go. Oh, that looks much better. Thank you for computers. They can do this much better than I could. Um, and this just, yeah, this just says what I said out loud a second ago. And that's it. So that's how you can sketch a hyperbola given that equation of it. Pretty cool stuff. Okay, now that we've finally talked about hyperbolas, we can continue our exploration of asymptotic analysis so that we're going to kind of pivot a little bit here. Again, this is largely for the computer science majors and just any kind of research where you're looking at asymptotic behavior, you want to have some understanding of asymptotic analysis. CS majors, you will study this and way more rigorously and in great detail in your major courses. So, asymptotic analysis is critical in computer science when time complexity is studied a lot. The amount of time that it takes an algorithm to run becomes an important point of focus. Yeah, it's just an important point of focus. The amount of time it takes for an algorithm to run is expressed as a function whose output value is determined by counting how many of these elementary operations the algorithm requires to run for any given input. Elementary operations meaning those ones that we talked about back in chapter 1, section 1.1. All right. Um, Common algorithms that you may have heard of before or even done yourself without realizing it are sorting algorithms, basically rearranging a set of data into a preferred order, and calculation algorithms like multiplication and division. I mean, we talked about the division algorithm a lot, right? That's an algorithm. So it's basically a process. And in this case, it's a loop that you can run and run and run and run. So the question is, how long will it take for that algorithm to run? And it may surprise you to learn that some algorithms, for example, integer factorization, can take a really, really long time to run for a computer to run or a human being to run. In fact, it may take so long that it's basically impossible for us to do. Yes. So imagine finding out some algorithm you've come up with is going to take, think about like a billion years, that kind of thing. Long, long time to run. That becomes prohibitive, and that algorithm is not really effective for our purposes, right? So computer scientists, what they do is they endeavor to develop new algorithms that run faster or have a better time complexity and basically save you a lot of time. Some of the classes of functions that we've seen already, they grow really, really slowly, just depending on the input, but some of them grow face-meltingly fast, meaning uh, kind of like the factorial function, right? Even if you just get a few steps forward in the input, the factorial function explodes extremely fast, right? So how do we talk about this different growth behavior, this different growth of these functions? We use something that's called big O notation. And big O notation lets us classify these functions in terms of their asymptotic behavior and compare it with other functions. All right? So here is the definition. Big O notation. It's a bit of a technical definition, but we're going to make sense of it right now. So let's say f is a function of interest, and let g be a comparison function. G is a function we're going to compare f with, both of which we're going to say are defined on some unbounded interval from a to infinity. So just, over there, basically, all the way to infinity, then we write this. We say f of x is equal to big O of g of x as x goes to infinity. And we say f of x is big O of g of x, or we say f of x is on the order of g of x if there exists a positive real number m such that this inequality holds for all x greater than or equal to a. All right. Ponder that for just a minute before I elaborate a little bit. So just kind of stare at that because that's a lot. Just probably be like, that's okay. All right. Okay. Now try to say some of this out loud. Just read some of the sentences, maybe try to phrase them in your own words. Okay. Oops. Now let's talk about it a little bit more. This inequality is really the crux of everything. Let me explain what it's saying. It's saying that the size of f is less than or equal to the size of g times some number m. So this is the definition of this right here. So if we say f is on the order of g of x, what it means is that the size of f is less than or equal to m times the size of g, and we can find m. Basically, the number m exists. There exists a number m that will make this inequality hold when x is sufficiently large, when x is large enough, right? That's the basic idea. So here's an example, and we're going to see several examples now. Let's take f of x to be 3x squared. Well, then we can say that f is on the order of x squared because the absolute value of 3x squared is less than or equal to 3 times the absolute value of x squared. So in this case, x squared is our comparison function. And we were able to show that this function f is big O of x squared because there's this number 3 where f of x is always going to be less than or equal to 3 times x squared, that comparison function. That's really all it means. Yeah, so this is saying that the size of f of x is bounded by the size of g for all x that are large enough up to some scaling factor m, which doesn't depend on x, all right? Um, if f of x and g of x are both positive, then what we say is that f of x is dominated by that value m times g of x. And you can actually use this notation to talk about local asymptotic behavior as well. Like if you want to talk about vertical asymptotes instead of just like end behavior stuff, right? You can do that. You just tweak the definition a little bit. Um, uh, yeah, so in either case, what this inequality is doing is it's giving us a way of comparing the asymptotic behavior of two functions, a way for us to kind of look at them and say, oh, this one is basically like that one over there. This function f that I'm interested in is behaving a lot like this comparison function when x is large enough. That's kind of what it's talking about. In practice, f is our function of interest. So maybe f is describing an algorithm we came up with or just some other function. And the comparison function g is one whose asymptotic behavior we already know. Like we know how g behaves. That's why we're comparing f to g. All right. Um, this type of analysis is very common in computer science. So a lot of times our functions are taken to be sequences. They're taken to be discrete functions. Little Mathematica note here. Mathematica also knows big O notation, not surprising. And it just uses the syntax big O of x to the n, like that. That's it. Okay, so let me see. Let me see. Okay, let's do this. I've got a couple examples here. I want you to try this example, or I want you to see if you can answer this question, but maybe not be able to justify it. If you want to try to justify it, you can, but let me ask you this question, see if you can answer it, and then we will prove it. We will prove what you're thinking, all right? So my question to you is, on what order is this function here, x cubed plus 9x squared minus x plus 4? On what order is it? Think about it for a moment. All right. And now say something out loud. What's your guess? All right. Now write it down real quick. What would you say this function is? F is big O of what? Okay. All right. Now here's the answer. F is on the order of x cubed. That's the short answer. So if you said that, you've got the right idea. In other words, f of x is big O of x cubed. And the reason for that is because we can establish that inequality that defines big O notation, right? So watch this process. This is an important process. You're going to see this a lot in Calc 1 and beyond. We're basically leveraging the triangle inequality and properties of absolute value. So I'm going to walk very slowly through it, and we're going to do this a couple of times, okay? So the absolute value of f of x is just equal to the absolute value of its formula. Now, by the triangle inequality, we can basically split up this absolute value. Remember, we may not have equality at this point. Okay, we may not have equality, but we do have an inequality. And the triangle inequality, maybe I'll refresh your memory here. Triangle inequality says this, right? The absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. So one of the nice things about an inequality is it gives us a lot of flexibility, and that's exactly what we're going to leverage right here. So this absolute value is less than or equal to the absolute values, I'm sorry, the sum of the absolute values of the individual terms. So absolute value x cubed, 9 absolute value x cubed. Well, maybe I should have put an intermediate step here. Yeah. Give me 1 second. Let me write this out and then I'll change it on the slides later. Hold on 1 second. All right, there we go. Thank you for bearing with me. I'll revise the slides after this recording and include this step just to make it a little bit clearer what's going on. So here I use the triangle inequality to show that this is less than or equal to this. And here's what I did. It's basically less than or equal to the absolute values of the individual terms, that sum. And what I also did was I converted any subtraction into addition. Why am I allowed to do this? Because we are working with an inequality. That's the power of an inequality here. This is not an equality, so it's not very tightly constrained, right? But certainly if I'm subtracting a positive number, that would be less than adding a positive number. So that's why that inequality is critical. And I use the triangle inequality to basically split this up as this sum of individual terms, right? Now we're going to go back down to here, okay? So now this is the step that's shown right here. This is just this, but 9x squared is less than or equal to 9x cubed, right? X cubed is bigger than x squared, right? When x is very large. So 9x squared is less than 9x cubed, and that's why we have this inequality right here. Same thing here, x is less than x cubed for large x, and 4 is less than 4x cubed for large x, all right? That's the idea. Why did I do this? I did this because now every term has a common factor of absolute value x cubed. X cubed, x cubed, x cubed, x cubed. Now I can combine all of these like terms. Here's 1 plus 9 plus 1 plus 4. That gives us 15x cubed. Now, mushing all of this together, or maybe ignoring all the intermediate steps, we've shown that the absolute value of f of x is less than or equal to 15x cubed, absolute value x cubed, right there. And that defines big O, right? This is saying that f of x is on the order of x cubed, and that number m is 15 in this case. That's it. So we can compare f to x cubed, and that's what it is. F is on the order of x cubed. And in this case, our comparison function is x cubed. That's the idea. Let me go to this slide. So here's some good news. In general, any polynomial of degree n is on the order of x to the n. So if you're wondering what is a polynomial, it's big O of the leading term. That's basically it. In this case, x cubed was the highest power term. So this whole polynomial is on the order of x cubed. This is that dominating term, right? We talked about that when we were talking about rational functions and using the division algorithm to get it written as a quotient. This is the dominating term. So that's dominating the asymptotic behavior, the end behavior, all right? And again, this makes sense numerically if you start plugging in values, large values of x. So for example, yeah, x squared, x, and 4, these things are all much smaller than x cubed. So for example, 1,000 squared is a million, but 1,000 cubed is a billion. So it's 1,000 times larger in this case. So this term is going to give you things that are 1,000 times larger than this term. So that's why this term is the dominating term, and that's why this function is on the order of that term. All right? Okay, we'll do another example in a minute, but let's talk about some common types of asymptotic end behavior. There's a lot of orders of common functions, but we're going to emphasize a few here. These are the ones that you will often see in computer science. So there are constant functions. Those are big O of 1. There are logarithmic functions. So if your function is big O of natural log, um, that means the comparison function is the natural log. There are fractional powers, big O of x to the m over n. In this case, we take m to be smaller than n so that your power is less than 1, because then the next order is big O of x. And in this case, that is a linear order. That's just the line y equals x. We've got this fun one. This one's called linearithmic. Some functions are on the order of x times ln of x, right? X times ln of x. Then after that, we have polynomials. I'm writing these in an order of increasing growth, and I'm going to show you the graphs in just a minute. But the next one is polynomials, x to the n. After them, you have exponential functions on the order of e to the x. After that, you have stuff that is on the order of the factorial function. And then you have this crazy one, the double exponential functions that are on the order of e to the x. All right, we'll see some graphs in just a moment here. So there is an order to these orders, and it's this right here. Basically, we're ordering these based on growth rate. The constant functions, their growth rate is 0. They're not growing at all, right? They're just constant. They're staying at the same level, not increasing, not decreasing. Now, the growth rate of all of the other ones is strictly positive, and their end behavior is infinity. So what I'm saying is all of these functions, natural log, x to the mn, x, x ln x, x to the n, e to the x, n factorial, e to the x, they're going to infinity as x gets bigger and bigger, right? They're going to infinity. The important point here is that some functions grow faster than the others. That is the important point. So even though the end behavior is the same, some of them grow way faster than the others do. Um, for example, linear functions grow faster than logarithmic functions. So that's why this one is down here and this one's up here. Linear functions grow a lot faster than logarithmic functions. You might remember I was mentioning that back in section 4.3, where the log graph, it does go to positive infinity. It just goes there pretty slowly. It goes there more slowly than even just a linear function. That's the idea. Um, a very particular result here that I want to emphasize, and computer science majors, you will need to know this well. Exponential functions grow faster than polynomial functions. Okay. So the reason that's important is because if you have an algorithm that runs in exponential time, it's not a feasible option for computers or humans to use. That's why we study these growths. That's why we want to be able to compare the growth of these types of functions, because if something you come up with grows exponentially, it's not feasible for computers to run. Polynomial is not so bad, though. Polynomial is not so bad. So for fractional powers, I said this already, we assume that the fraction is less than one. So for an example of this big O right here, you could think of x to the 1/2, which is the square root of x. And the reason we do that, the reason we require that this fraction m over n be less than one, is if m over n were bigger than one, then we could just compare it to a polynomial instead, because by Euclid's division lemma, once again, we can write this fraction as a quotient plus a fractional part. So if this thing is bigger than one in size, we can basically pull out this, this quotient, and we could just use that as our comparison instead, right? And that would be polynomial in nature. Um, Here's another result here. Exponential growth is already almost unfathomably fast. It's really, really hard for humans to understand just how fast exponential growth really is. It's just really hard for us to wrap our heads around it. But the factorial function grows faster than any exponential function. So the factorial function is blowing up even faster. And then a double exponential function grows faster than all of them. More generally, you can talk about what are called tetrations, which are basically powers to powers to powers to powers to powers. That's called a tetration. Just face meltingly fast. They just grow so insanely fast. It's unbelievable. So let's look at some graphs, because this is a lot of algebra. This is a lot of like inequalities, a lot of like stuff like that. But the picture, I think, really hammers it home. So here's the picture. I'm going to zoom in a little bit. First, at the bottom here, you've got the constant functions. There we go. Big O of one, constant, no growth at all. Right above that, you've got big O of natural log of x. Remember, natural log is the best log, so that's why we just say natural log. Um, yeah, another thing I will remind you all, when we're talking about end behavior and asymptotic end behavior, we're thinking about when x is huge. X is trillions and trillions, quadrillions. We're not really concerned about when x is one or two or five. We want x to be extremely large, okay? So natural log looks like that. So it's growing faster than no growth. Then we have fractional powers. Think things like square root of x, cube root of x, that kind of stuff. Then the next step up is linear, right? There's that diagonal line. So linear functions grow faster than logarithmic functions, for example. Then right above that, you have you have linearithmic. So linearithmic is this one right here. That grows faster than linear. And that makes sense too, because remember, think about when x is large, we're talking about taking x and multiplying it by natural log of x. So using like that graphical arithmetic we talked about, this is going to be greater than both of these things, right? Both of those things. After linearithmic, we have polynomial like that. And then after polynomial, we have exponential. And again, even just looking at this graph, exponential functions grow insanely fast. So here we're at what? If this is five, this is about what, two or three maybe? And we're already way up here. Already way up here, not three, but we're already way up there. So pretty large. Now, in order to even talk about how to compare the factorial function and the double exponential, I need a second graph. So let me go to that one. Okay. So now I had to change the scale of everything because these things grow so insanely fast. So what I've got here is the exponential function. It's this red one that you see there. And then here you'll notice that the factorial function starts getting, it dominates the exponential function when you get to about here, right? When you get to about there, all right? And then what's growing even faster than that? The double exponential, boom, just shooting up almost instantly. This is the number one. So this is e to the one. And that's how high it is already, like if you kind of trace it up. Can you even imagine e to the two? It's somewhere on there, but it's probably like way, way, way up there. Okay. So that's why this order is important. This order is important. And really what we're looking for is we're looking for the largest one of these orders, right? The largest one. So if we have a function where there's a whole mix of these different types of functions, typically we're going to pick the largest one, and that'll be our comparison function. Okay. All right, let's do another example. And here's one that I want you to try on your own. If you can't do it, no worries. We're going to do it in activity. You're going to get practice on the homework. But I want you to determine what order this function is. And I want to see if you can prove it the way we did the previous example. So use the triangle inequality, use properties of absolute value, and so on. So on what order is 3 times square root of n plus natural log of n? On what order is that function? All right, now verbalize your guess. Just say it out loud. Maybe when you say it out loud, you'll be like, maybe that doesn't sound right. That's why we do that, to say things out loud. Okay, now try to work it out. So if you have a guess, see if you can prove it using the techniques that we did in that previous example, okay? All right, now let's do it together. So the basic idea is this. We want to pick a comparison function that will dominate all of the functions that appear in this expression. So we've got, what is that? Square root of n and natural log of n. Okay, so which one of those grows faster than the other? That's really the question, right? Well, excuse me, natural log grows slower than square root for all n greater than 0 in this case. So here's a comparison of those two graphs. Here's natural log, and here's the square root. All right, so the square root function here, that's the dominating function in this expression here. So that's what we're going to use as our comparison function. We're going to use square root of n. So just like before, we're going to take the absolute value of this. We're going to use the triangle inequality to split it up, and then we're going to pull constants out. That's the basic idea. So here, this is going to be less than or equal to this. And now what we're doing is we are replacing all instances of natural log with square root of n. We're allowed to do that because we've got an inequality going on. That's an inequality. Now we're going to combine like terms. 3 of these plus 1 of these is 4 of those. And now we've done it. This is 4 times n to the 1/2 for an absolute value, right? So we can say that this function is on the order of square root of n, on the order of n to the 1/2. That's it. That's the idea. Okay, let's do one more example. This one, I'm mixing all sorts of stuff up, okay? So I want you to try this one again. See if you can determine on what order is this function. What order is that function? Stare at it for a minute, right? Okay, now at least make a guess. On what order do you think it is? Okay. Now see if you can prove it. My hint to you is look for the function that grows the fastest. That's going to be our comparison function because whatever that thing is, it's going to be growing the fastest. It's going to be growing the fastest, and all the other stuff will grow more slowly. So we need to pick the one that grows the fastest. Okay. All right. Now let's do it together. Let's look at some things. Okay, I see a fractional power here. Oh, but then I see a polynomial term here, right? So This is already the biggest one. As I go through, this is the biggest one so far. Log is actually even slower than this. So that's not the bigger one. Oh, but then right at the end, we've got that exponential, that 2 to the n. That is the dominating term. So our comparison function is going to be 2 to the n. 2 to the n grows faster than this and this and this. So long story short, f is on the order of 2 to the n. Now let's prove it using the triangle inequality and absolute value. So here we go. We're going to take the absolute value of our function. Triangle inequality will let us split it up into multiple pieces. So we're going to replace all of these with 2 to the n's. So this is being replaced with 2 to the n. This is being replaced with 2 to the n. This is being replaced with 2 to the n. And this is remaining as 2 to the n. Absolute values from the triangle inequality, boom, 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 boom. And now we can just combine like terms. 1 plus 7 plus 1 plus 1 is 10. And there it is, we've shown it. F of x, or I should say f of n, is less than or equal to 10 times 2 to the n, absolute values, right? So that means f of n is on the order of 2 to the n. And that's the idea, okay? So that's big O notation. Little bit of some notes, some stuff that you'll see on the mathematical horizon. Uh, in computer science, polynomial algorithms that have low exponent values are considered to be efficient, okay? So if your algorithm runs in polynomial time, it's considered to be efficient. Exponential algorithms are considered to be infeasible due to how much time the algorithm takes to run. So if an algorithm you've come up with or a process you've come up with is exponential in nature, it's not really something that computers can handle. It's just it just takes too much processing power, too much time to actually get through it. Okay, here are some good examples just to kind of give you some context. If you wanted to think about multiplying two n-digit numbers using standard multiplication, think about a 20-digit number times another 20-digit number. Well, the standard multiplication algorithm that you learned back in grade school, it's on the order of n squared. So it's actually pretty efficient. That square is not the n squared is uh, not a coincidence. Remember, every multiplication can be represented as an area, right? So if your numbers have the same number of digits, then you end up with a square. That's why it's n squared. That's really what it's doing. So multiplying two numbers is actually pretty efficient. It's just on the order of n squared, right? However, compare that to this. What about an algorithm for producing the prime factorization of a given n-digit number? Remember, we practiced factoring a lot in chapter 3, and you can kind of see that it was not exactly the easiest thing to do, right? Well, a common algorithm for doing that is on the order of 2 to the n over 3, which is very infeasible when n is large, okay? When n is a large number, meaning you have a large digit number, think like, man, think like 100 digits or 1,000 digits or a million digits. If you wanted to factor that number, it's going to take a really, really, really long time to do, right? Really long time to do. So factoring is not easy. Factoring numbers is not easy. We saw that before. This is why computer scientists constantly strive to come up with better factorization algorithms. This is actually also why factoring prime numbers and the difficulty associated with that is a cornerstone of modern cryptography and cybersecurity. The idea is you deal with extremely large numbers that are extremely hard to factor. And the only way you can crack the code would be to factor that number, right? Because that is such an infeasibly long process. We use it to encode a lot of things. So modern cryptography is based on prime factorizations and cybersecurity. I will say that's just for now. Quantum computing is coming in and kind of upsetting that because quantum computing lets us do things faster than we could before. So, yeah, there's a lot of research going into that right now. If you're interested, you can dig into it, dig into cryptography, read some articles about it. You can read about quantum computing because that's kind of turning a lot of stuff on its head at this point. Um, yeah, so if it were easy to factor a number, all of our current cybersecurity measures would fail. So that difficulty that you felt with factoring a number earlier on in the course, that's a universal feeling. So don't feel bad if you're like, oh my gosh, this is so hard. We know it's hard. And in fact, it's so hard that we base our cybersecurity around that difficulty itself. Okay. All right. That's enough of me rambling. On that note, let's play. All right. This is a fun section. I know it's a little bit more technical than the others, but you will see this stuff a lot. It's important information. CS majors in particular, you want to know this stuff. Okay. I'll stop there. Thank you all again for watching, and I will see you next time when we talk about summations. Have a good one, everybody.